W10, double slit interference. Now we've already seen that if you've got two sources in something like water waves or sound waves, then you can get them to overlap because they diffract as they go through the small gaps and superpose to give a stable pattern of high points and low points. The key thing is that you need two coherent sources. So just pause a minute and remember what coherent means. It means that they have to have the same frequency and a constant phase difference. Okay. Now that's very difficult to arrange with light because most light sources are quite random and it's very difficult to arrange them to be coherent. So the solution is to just use one source here and let it become two sources by putting it through a double slit like this. So the wave hits each slit and diffracts again on the other side, and the two sort of spreading waves overlap and can then produce a pattern. So this leads us to an equation. So here's a double slit at this end, and it's so tiny to get it to work with light that you can't see it on the scale of this drawing. But imagine there's two slits here, and there's a beam of light travelling across a fairly large space and hitting a screen at this end. So what you see on the screen would be a pattern like this, and these are called fringes. So the bright points are the bright fringes and the dark points are the dark fringes. So how does that happen? Let's think about the first fringe from the centre. If we construct some lines, so one line to the middle fringe and one line to the next bright white fringe out, then there's an angle between them, and we call that theta. The first fringe in the middle is called the 0th order fringe, so put a 0 there. The next one is called the first order fringe, the second order fringe, and so on. And you could also number them in the other direction, so you've got 1 and 2 on that side as well. So when we talk about the nth fringe, you just count from the middle, assuming that the middle one is 0. Okay, now the distance between two fringes is called the fringe spacing, and it's given the symbol W. Okay, and the other thing we need to have a symbol for is the distance from the slits to the screen. Call it capital D. So if you look at the triangle that we've made here, you can see that tan of theta is the opposite over the adjacent, so that's W, the opposite over the adjacent D. So that's one equation. Now to get another one, we need to zoom in on what's happening actually at the slits. So let's draw those a bit bigger. So the beam that's making the 0th fringe heads off straight towards the screen. And the beams that are from the two slits that are forming the one going up here are travelling at this angle here. I've exaggerated it slightly just so it's a bit more obvious. So these two beams are going to diffract, spread out and overlap before they get to the screen and combine together. So they're heading off at an angle theta to the horizontal. If I draw a line perpendicular to them, their direction of travel here, so perpendicular, so I draw the right angle in there, and if we just label here with the distance between the two slits, we'll call S for slits, that's easy to remember. Then in order to make a bright fringe over here, the two paths must be in phase. Now they're obviously in phase in the middle here because they've both travelled the same distance to get here. But to get to this one, the first order fringe, the beam from the bottom slit in this diagram must have travelled a little bit further than the one from the top slit, and it must have travelled a little bit further by exactly one wavelength. So they're back in phase again. So they both arrive together with their peaks and troughs in sync, so that they can add together and give a big result. So let's just draw that direction again. So from the top diagram, we've got the angle theta here to the first bright fringe, the fringe number 1. We've got two parallel lines here, the dotted ones. So if this angle is theta, so is this one, alternate angles. If you look at this triangle, okay, if this angle is theta and this angle is 90 degrees here, then this must be 90 minus theta, the one I've drawn with two lines. And then if we look at this triangle here, if this is 90 minus theta and this angle in the corner here is 90, then this angle here must be theta. So there's a theta as well. So if we take this triangle once again, okay, got theta in the corner, and we've got two distances that we know. So we can write that sine theta is the opposite, lambda, over the hypotenuse, s. So we've got a second equation. Sine theta equals lambda over s. Okay. So two equations. Tan theta is w over d. Sine theta is lambda over s. Now, it turns out that for very small angles, tan theta is the same as sine theta. And if you want to test that, try doing tan of 1 degree on your calculator and sine of 1 degree, and then maybe tan of 0.1 and sine of 0.1, and you'll find very quickly they become absolutely identical answers. So if they're both the same, we can equate those two parts of the equations. So the w over d must be the same as lambda over s. And all we need to do then is rearrange it slightly, and we get a formula that says lambda, the wavelength of the light, is w times s over d. So it's the spacing between the fringes, w, times the spacing between the slits, s. They're the two small measurements in the apparatus, divided by the distance to the screen. That's the large measurement. Now if you think about it, the fringe spacing is reasonably easy to measure. Distance to the screen is also easy to measure with a ruler. The tricky bit is getting two slits very close together, which are where you know the distance between them accurately, but that's the only tricky bit really. So you can measure the wavelength of light, which is a tiny, tiny quantity. It's about 600 nanometers for red light, with basically a ruler and just a careful bit of measuring. Now it's Thomas Young who first did this experiment back in 1805. So that's why it's called Young slits.